I mean, right now I have the current week set up for the tissue level stuff. And I'm going to leave it that way, even though we're starting the skeleton stuff, because the tissue assignments, I didn't make it due until next Sunday. Just since we just did it on Monday, I thought it was kind of cruel to have them due 2 days later. Actually, you should have finished the cell biology stuff by last night. That wasn't necessarily due to last Sunday. I set it for last night, but so that'll get us on course. And then the skeleton assignment stuff will be due later on. And actually, let me go to that folder because I just want to remind myself of when I set that. Come on. That's kind of funny. Come on, you can do it. So hopefully this will be the bone folder in a second. It is, okay. Skin and bones. Anyways. So I believe the learning pod assignments are going to be due for Monday night, right? Or were they due last night? I mean Sunday night, yeah, before next Monday. All right, the computer's just freaking slow today. And then, so the other assignments, the chapter assignments and that stuff are due before the next class meeting. Okay, yeah, so the learning pods that actually have to do with the chapters we're starting now, I've actually made due on Sunday night, just again, so that you didn't have too much stuff piling up all at once. And then the big question, also because we're doing 2 chapters worth of stuff, so there's a bit more to do. There's 3 learning pods on the skin, and then 3 learning pods on the skeleton. Because of when I was setting all this stuff up, learning pod had some issues one week when I was doing all this. So I was setting up learning pods for the skin stuff, and I made one about the epidermis, one about the dermis, and then there's the one about the chapter. And then when I went in to do the same thing for the bone chapter, learning pod wasn't working that day that I was trying to get on there. So there aren't any short learning pods for the bones. So this is the learning pod for the bone tissue chapter, which is chapter 2 in unit 2. And then this is actually the learning pod for the next chapter. And this is the learning pod for the next chapter after that. The chapters 3 and 4 in unit 2 are about the axial and appendicular skeletons, axial meaning the body trunk and appendicular meaning the appendages or your arms and legs. Those chapters are not going to be, what's the word I'm looking for? Lecture type chapters. There's not part 1, 2, 3, 4 assignments for those chapters. It's really just the laboratory material. And so because Learning Pod wasn't working the particular day I was sitting down to set up the learning pods for the skeleton chapter, I came up with the idea of just assigning those 3 learning pods that are already there for those chapters. So there aren't any additional short learning pods for this. There's just the 3 chapter ones there. And I did that really because I wanted students to look at those chapters. That's the material for the laboratory stuff that we're going to be doing on Monday. So you won't have assignments about those 2 chapters other than the learning pods there, but it is stuff that I want you to get to. And then, so all of those learning pods, those 4 learning pods need to be done by Sunday night. And then there's skin parts 1, 2, 3, and 4 about the integumentary system. And then bones part 1, 2, 3, and 4 about the bone tissue chapter. So that's chapter 2 in unit 2. There are no other part 1, 2, 3, and 4 assignments about the skeleton having to do with the other chapters. The axial and appendicular skeleton chapters are just for lab material. Okay. So you have 2 chapters worth of stuff in this folder. Now, what I wanted to do was to just open one of these up and verify when the due date is. And the due date, in fact, is March 22nd at midnight. That is the Sunday at the end of spring break. Okay, we're doing this material starting it today, but it's basically Monday's class material. And the following week, you're doing the practical. So there's no point in making the chapter assignments due the following week because we're not doing another chapter that next week. So I decided to put it off until our next class meeting. It's just that our next class meeting happens to be on the 23rd, which is the Monday after spring break. So those things are due actually sort of 2 weeks, 3 weeks out, whatever it is, which I hope kind of mitigates the fact that you're doing with 2 chapters in the same week. You also have plenty of time to work on them. Okay, yeah.
So nothing on the tissues that's due on the 22nd will not go into our like mid grades.
Okay, so yeah, midterm grades. Let me just say something about that. Midterms or grades are due.
15.
No, I think it's the 12th. Midterm grades are basically me saying, here's what grade anybody has on the exact midpoint of the semester. And so all I do is I go into Blackboard and whatever the overall grade says you have, I put that into the system as a letter grade. So if you have a 75, you have a C. If you have an 89, you have a B+, whatever it is. It goes in there based on the letter grade scale. I don't really care too much about midterm grades. They're not that important, and they're actually kind of stupid. It's not a real midterm grade. It's not like half of the work for the semester, exactly. It's just I have to sit down and write whatever's in there. Now, actually on the 12th, which is when they're technically due, when I have to put them in the system, I'll be in Chicago for this conference. I'm flying out on the 11th. So I'm actually going to post them on the 11th. Not that that makes any big difference, but so I'll just, whatever grade you have on Blackboard at that point, that's what goes in. The point of midterm grades is just to help with advising. So when you go to register for next semester's classes, your advisor and you will sit down and look at how you're doing. If you have an F as a midterm grade, then they should say, well, you might not be ready to go on A&P2 or something like that. The problem with midterm grades, the reason I don't really care for them, is that they're not a terribly accurate representation of anything. I've had plenty of advisees who come in that have, say, an F in psychology. And I asked them about it, and they said, oh yeah, I just didn't turn in something before the midterm date. But as soon as they got that thing in, since that was kind of the only grade that their test was, that was the only score that the grade was based on, once they turn it in, the F became a B, or something like that. So the midterm grades aren't perfect reflections of actually where you are at any particular time, but that's the way it works.
And like my grades, link has like all of my grades.
So yeah, when you click on that, which I can't do because not being a student myself, when I click on my grades, it says you don't have any grades. But when you click on it, you'll see a list of all the assignments. I'm not sure if it lists all of the assignments for the entire semester or just the ones that are due or past due.
I think there's like an all and a graded.
Okay, so you can look at different things. So you'll see at the bottom there, it'll have your lecture score, your lab score, and your overall grade. Okay. The lecture score, well, it's easier to explain the lab score. The lab score is your lab grades and the practicals. Okay. And then lecture is everything else. For you, at the point of midterms, I will not have your first practical graded because there's an online component to that. So that won't go in to the system until after midterm grades are due. So your midterm grades lab score will really be based on any lab quizzes you've done up to that point and the microscope practical. That's not a very good reflection of things. Let's say you only did 2 lab grades, 2 lab quizzes, and you got 5 on one and 4 on the other. That's 9 out of 20 points. That's a failing grade. It's not at all an accurate representation of what's going to happen by the end of the semester because there's a lot more grades to go into that. That's what you're graded on. Now, the way that the grade book works right now is any assignment that you've completed and I've graded or has been autocorrected, it counts. Anything that you have not done or that you might have done and I haven't graded doesn't count. It doesn't factor into your grades until it's completed. It just ignores that grade completely. So you're only being graded based on what's there. At the end of the semester, when everything's done, I'll change that so that everything counts. And if you haven't completed something, then it'll go into the grade book as a 0. But at this point, anything you haven't done doesn't factor into your grade. If you haven't done any work, technically, then nothing will count against you. Now, in fact, if anybody in the class hasn't done anything by midterms, I give them a midterm grade of an F just to reflect they haven't done any work yet. But I don't think anybody's in that situation. Everybody's done something. So if you've done one thing, whatever that equals as a score, that's your current grade. Okay. It can be a little misleading just because that's a slightly artificial way to look at grades, that not completing something yet doesn't count as a 0, although that's the way it'll work at the end of the semester. So midterm grades are a little bit rosy looking. For A&P 1, that doesn't really matter because for A&P 1, you're really just looking at the midterm grade to decide whether you're ready for A&P 2 or not. In A&P 2, that's a bigger deal because unfortunately midterm grades are used often for people that are applying to a program. They look at the midterm grades when they're making the decision because they don't have the final grades in time, which is really more of a deal for people that are taking A&P 1 in the fall and A&P 2 in the spring. So it really isn't going to affect any at all. But midterm grades for A&P 1 really aren't a big deal.
It is A&P offered.
Say that again?
Is A&P offered?
Yes. Yeah. Sorry?
It's a suicide mission.
Well, there's two ways. There's a couple of ways you can take it. The summer's set up into 2 sessions. There's 5 weeks for session 1, 5 weeks for session 2. You can take it in the more traditional lecture format, which would be 4 hours a day, 4 days a week for 5 weeks. And that's the suicide mission. Okay. We're starting to offer it in different ways. One is that I offer this version of the course, the hybrid version of the course, where you just come in once a week for lab. And over the summer, distance courses, which is what that counts as, go for the whole summer. Okay. So if you've got A&P 1 under your belt here in the spring, you can sign up for A&P 2 over the summer. It's not quite as much of a suicide mission because it's 10 weeks long, which isn't that much different from the 14-week semester that we have regularly. There are a few things that go a little bit faster, but it's also 4 hours a day instead of 3 hours a day like we do now. So we kind of cover the same amount of time. Also, I think they're starting to offer a 10-week version of the regular lecture where you come in twice a week for 10 weeks instead of 4 times a week for 5 weeks. The thing about the 4 times a week for 5 weeks, which doesn't apply to any of you, is if you want to take A&P 1 and 2 both over the summer, you could do that. Again, suicide mission. But for you, if you're looking to take A&P 2 over the summer, I definitely will be offering it as a once a week for 10 weeks thing, same kind of format as what we do here. I think somebody else will be offering it as a more traditional lecture style class, 2 days a week for 10 weeks. I think those will both be offered. So, were you about to ask a question?
Yeah. When are they going to start allowing people to go in and
register?
Yeah.
So priority registration is the same for summer and fall. So when you sign up for fall stuff, you can sign up for summer. I don't remember the dates offhand, but if you go into the academic calendar, it'll tell you when those are. It's usually like the last week of, no.
I'll tell you in a second.
It's usually early April, somewhere in there.
I think it's April 4th.
That would make sense. 5th?
Back to 11.
Okay, so the way we do it now, the 2 weeks before that is advising period. So you can get in and talk to your advisor, decide what you want to do. Your advisor will unlock registration for you, and then you can jump on it right at 12:01 on the 5th, is that what you said? Whatever the first day. So you can go in at midnight and sign up for your classes immediately if your advisors pre-approve you. Otherwise, during that 5th to 11th, you can go and meet with your advisor and sign up for stuff.
If we are not in the associate degree program, I'm just taking some classes.
In what program?
I'm not in the associate degree program. I have a bachelor's. Do I have a quote advisor?
All day students have advisors. You should get a letter, if you haven't gotten it already, it'll be coming the next week or two, saying who your advisor is. And technically, probably none of you are in an associate's program right now. People are taking prerequisites probably to get into an associate's program like nursing or something like that. Or there might be people that are already in like surgical tech or something like that. Basically, everybody here is sort of in that undecided kind of state right now. Yeah.
Just hypothetically speaking, this is nothing against you because I'd love to take A&P2 again in the summer. And I'm applying to like a second bachelor's degree program. Would this A&P1 transfer over if I could take like A&P2 at UMass or something? Or does it have to be 1 and 2 at the same school?
I believe it will transfer. I can't speak definitively on any of that stuff because I'm not in the transfer office, but I'm pretty sure it will transfer.
Okay.
Usually the problems people run into more are not transferring from here to four-year college, but rather classes they take here. And the big one I hear about is medical school. So sometimes medical schools won't take community college courses as prerequisites, which offends the hell out of me.
And I think community colleges in many aspects are much better for like.
Yeah, if you're taking A&P at a four-year college, you're probably taking it from a graduate student who's trying to do his classes and his research, and I'm saying him because I'm imagining it's me, which I was doing when I was a graduate student. Or you're taking it from a professor who, doesn't really pay much attention to teaching because their whole job is based on the research they do and the money they bring in with grants. So at a community college, that's not how it works. We're here to teach. And so we can put more time into what we're doing. I have the exact same credentials as a professor at UMass would have. I've got a Ph.D. I've done postdoctoral research, all that stuff. I just didn't want to do research for the rest of my life. So I came here.
But I didn't mean to offend
No,
you.
I wasn't offended by you. I'm offended by the medical schools that think that
Yeah.
I'm not as good as somebody at UMass. But
I know a lot of PA students that went here.
right. So for you, I would, just to be sure, talk to UMass and make sure that that's okay. I've certainly had people that have been here to take to AP1, and then they go to some other school and they come back here to take AP2, just so they sort of have the continuity between the two. Sometimes what can happen is we end A&P1 at a certain point and another school ends at a different point. And so when you start their A&P2 class, you aren't going to have the exact same thing that their A&P1 students had. So sometimes the continuity does help. And it's not unusual for people to do that, to come back here to take A&P2 over the summer, even though they're currently in some of the program. And I've had students over at AIC that just don't like the A&P teachers over there, and they'd rather come back over here. So it happens. Anyways, so what I have on the screen here, now that we're back to thinking about what I'm recording, the due dates for all the stuff that technically is Monday's class. So you actually have some time to work on that. It's not going to be due by the following Monday. Okay. There is one thing, however, there's an axial skeleton lab quiz, and the lab quizzes are due before the next lab meeting. And the next lab meeting, so let's see, we'll be doing the practical. Oh, actually, no, that's right. So we'll be doing the skeleton on Monday, the 3rd, 2nd, whatever it is. And so that will be due before the practical. So that will be due the following Monday. But everything else in this folder will be due on the 22nd. Okay. Just, I want to be sure everybody's clear on that, just because we're not doing more lecture material that following week, so I'm not having any lecture material due until after, well, the end of spring break. Yeah.
Is our last class the night before the spring break?
Yes. And just that week, the 9th through the 12th, 13th, whatever it is, that's last week. And since you're on a Monday, you're going to be on the 9th. And the next Monday, which would be the 16th, is the Monday of spring break. So, yeah, that 9th is the last one before spring break. And then the 22nd is the Sunday at the end. So the 23rd would then be your next class. Yeah. Sorry, Tana.
How much time do we have to take practical?
I haven't talked about the structure of the practical at all, right? Okay, so let me do that now. Now, we did look at a case study which came out of the practical folder. So I've shown you where the practical folder is, and I hinted at least that it has something to do with case studies. So let me go there and talk a little bit about that. Now, a practical exam is usually thought of for, sorry?
I did do this.
I did the spiel.
Yeah.
Oh, no, I know what I'm thinking of. I haven't done it for my AP2 classes yet, because
You
They're
were over it a week
weeks out.
early with us.
right. So I did all this stuff. I
Yeah.
talked about 50 multiple choice question. Okay, good. I don't have to do that again. So actually, ask your question again.
Just how much time do we have to take it?
So the in-class portion, that's all we're going to be doing that week. And it should be complete within about an hour. It's designed to be taken in about an hour. But you'll have, if you need it, an hour and 50 minutes to do it, which is how long a regular lab period is. So that's just the limit I always put on it, which means we'll start at 1:35 and I'll kick everybody out at 3:25. Okay. We're not doing anything else that week. We're not going to stick around for that last hour to do something else. So when you're done with that test, if it takes you 45 minutes or an hour and 45 minutes, whatever, when you're done, that's it for the day. And then as that question applies to the online thing, that's due probably on the 22nd also. And again, you can always check that by looking at, yeah, so it's the 22nd there. Okay. You can go into this assignment now and start looking at it. And when you're studying, you might want to do that just so it gives you a little idea of what the cases are about in a little bit more detail. You can answer any questions you want. You can save answers, come back later on, whatever. Or you can leave it all till the 22nd, do it last minute, and not do very well on it. Your choice. So, other questions about the practical? Yeah.
The in class is the 9th?
Yes. So yeah, again, next Monday, the 2nd, is when we're having the skeleton lab. And then the following Monday, the 9th, is when we're doing that practical here in class, which will only be, that's the only thing we're doing that day. So when you're done with it, you get to go. And then the following Monday is spring break. And then the following Monday, we come back and we do joints. Okay. Everybody's clear on the schedule here? Okay. Now that the snow day catch-up stuff is all done, we should be a little bit more regular. But make sure everything's good with that. Okay, so what I want to do with our time today is to sort of introduce the skin and bone chapter material. And then next week, we're going to concentrate on getting to know the skeleton better. I'll actually give you some lab material today before you leave, which you could make use of as you see fit. But the Unit 2 in the book, we're now moving from the sort of foundational material that's chemistry, cells, and tissue. And now we're actually moving into organ systems. And so the first organ system we deal with is about the skin. I don't really care about the skin too much. I mean, the skin's an important thing. If we didn't have it, it'd be very uncomfortable. It does a lot of very important things. But as far as a topic in this class, it's not terribly interesting. And I think this chapter is best used to consider how we transition from that foundational material into the organ systems. Now, back in chapter 1, there was explanation of the levels of organization, the chemical level of organization, the cellular level of organization, the tissue level of organization, that kind of thing. The next thing that we get into after those levels of organization is into the first of our organ systems. And really for the integumentary system, the skin, what I think is best to concentrate on is how the chemical cells and tissues that we focused on in the first unit come together to make up this organ system. And when we think about an organ is going to be made up of multiple tissues. You can find examples of all 4 of the different types of tissue in any organ. And what you really need to think about, and this is going to really be true throughout the rest of the course, A&P1 and A&P2, is to think about how the tissues are related to the function of that organ and therefore the organ system also. So there is a section in the chapter on the skin that says functions of the integumentary system. Since I like stressing this idea of tying the tissues to the functions of the skin, I like to kind of put this up front. And so obviously the most important thing is the protection that the skin provides. What tissue do you think is most important about that function in the skin? Yeah, it's an epithelial tissue. And within the types of epithelial tissue, there is one that is pretty much just for protection, which is what? That's relative to it, but we're talking about types of epithelia. What do we call the epithelium? Remember layers and cell shapes? So it's a squamous epithelium because it has some flat cells in it, but is it one layer of flat cells or is it many layers of flat cells? Yeah, so it's a stratified squamous epithelium. When we're talking about a stratified epithelium, the cell shape tells us what type of cells on the top layer. Okay, there might be all sorts of cell shapes present, but the name tells us that the apicalmost layer is flat cells. As Aaron was saying, it's specifically keratinized stratified squamous epithelium. There is also non-keratinized stratified squamous epithelium, but stratified squamous epithelium is all about protection. It's all those layers of cells that are able to protect whatever they're covering or lining from problems in the outside world. So the skin is keratinized stratified squamous epithelium, but the lining of the esophagus and the oral cavity and the pharynx, which is your throat, the vaginal lining, the anal lining, all of those are stratified squamous epithelia also because they're protected. Okay. All of those that we usually think of as being inside the body are non-keratinized. They're softer, but they're still very protective epithelia. The reason that epithelium is mostly protective is because it's a really thick stratified epithelium. And you shouldn't see stratified epithelia that thick because epithelia are avascular. I talked about that last time, right? Yeah. So there's no blood vessels in epithelia. And so they get their blood supply from the areolar connective tissue adjacent to them. There's that set up in the skin and these other places too. It's just that there are some cells that are too far away from the blood supply, so they're dead. but they're dead on purpose. The keratin actually is what holds those dead cells in. And it's a very protective outer coat because you can't hurt cells that are dead, okay? This is a little gruesome, but if you're in a war, you would do better to hide behind dead bodies than to be out in the open and have people shooting at you. Okay. Gruesome, I understand, but you can't kill somebody more than they're already dead, right? You can't damage tissue any more than it's already dead. You can burn the outer layers of skin. It'll damage the cells, but they're already dead. You can't really do anything worse to them. You can spill acid on them. You can spill other noxious chemicals on them. You can freeze them. You can burn them, et cetera, et cetera. The dead layers of cells are there to act as a barrier, a protective layer that can't be hurt anymore so that the living cells below them are going to remain intact. So that's largely what it's all about, protection. Okay. Then an important part of the skin is its sensory function. And basically, there's only one type of tissue that can ever provide sensory function to us. What would that be? Any ideas? Right, nervous tissue. So all of your sensations are relayed to your brain, and you perceive them because of the nervous tissue. And there are nerve endings in the skin that make it possible to react to stimuli in your external environment. Okay, so that function is really because there are nervous tissue in your skin. A very important function of skin, which almost makes me guilty for saying that I don't care about skin, is thermoregulation, which means maintaining body temperature. Skin is very important for that. So what tissues do you think would be most important for regulating body temperature? So if we're talking about the four major types of tissues, and we can even separate down to smaller types.
Muscles, because when you like exert yourself, and you obviously get hot, and conversely, if you get really cold, you shiver. So muscles are producing energy.
Now, we're talking about the skin. So if you're talking about shivering, shivering has nothing to do with the skin. That's about skeletal muscles.
I think you were saying what were really for
Well, what I'm asking is, we're talking about the skin, and we're talking about the tissues and how they relate to these functions. So the stratified squamous epithelium is why it's protective. It's not all, but that's the major part of it. And then sensory function is because of the nervous tissue there. So in the skin, what tissues make it possible for us to regulate body temperature? And a lot of people will go there, and I'm not picking on you, that, well, when you're cold, you shiver. So obviously muscle has something to do with it. But when you're shivering, that's your skeletal muscles moving. It doesn't have anything to do with the skin. So the shivering isn't part of the skin's role in thermoregulation. So what in the skin do you think is going to be important for thermoregulation? Whether you're hot or cold, what happens in your skin?
It would be it's the pores, like all the cells come together to when you get cold, your skin like almost all the pores close, and you I'm not sure what the correct term for it is, but in you can see the difference between like skin that's warm, has a lot of blood flowing to it and things like that.
Okay.
And then
So how do you know when you look at skin that it has blood flowing to it? What tells you that?
The,
Go ahead.
Oh, it's pink.
It's pink. It's got reddish color because there's a lot of blood there.
so
Okay.
the nerve cells.
Sorry?
So the nerve cells.
No,
The Merkel cells.
No. It's Merkel cells are about sensory sensation. But if you're hot and your blood becomes pink, I mean your skin becomes pink because blood's flowing to it, that means that blood vessels are opening up and letting more blood flow through.
So,
Okay.
but didn't you say it's painful then? I would think that
Not painful, pink.
What?
Pink,
Oh, pink.
Yeah. the color. So you have blood vessels in your skin, and when they dilate, it's because smooth muscle in the walls of blood vessels relax. Okay. And when you're cold, the exact opposite happens, which is your skin gets pale because there's less blood in it. Okay. And that's because the smooth muscle in blood vessels contracts and forces the blood out of the skin. And it goes actually below the subcutaneous fat, which acts as an insulator. I'm trying to kind of go back where you were, Aaron. You're talking about pores, but actually I don't think you meant pores,
Yeah,
or
it's
not about pores. Sorry?
Like your hair follicles.
Yeah, it's about the hair follicles. Now, pores are associated with hair follicles, but it's not the pores. But I think what you're trying to describe, when you're cold, what happens to your skin? And it has a little bit to do with hair follicles. Get goosebumps, right? Now, goosebumps are really hair follicles that are moving, but there's no hair in the follicle. So whether there's hair or not, hair follicles are going to move to make hair stand up. Okay, and when you don't have hair in the follicles because they're not growing hair at that time, what you have is just a goosebump. Okay, but movement of hair follicles is because there's smooth muscle in the dermis that physically moves the hair follicle, makes it stand up. Okay. Sorry?
It's a erectile pillar muscle? Is that
Erecti pillar, right. Erecti pilla, rector pilli. But actually, interestingly, in humans, that doesn't do anything for us. We see it when you're cold, you see goosebumps, you know, it's a York peppermint patty commercial, that kind of thing. But it doesn't actually do anything for us. It's a holdover from organisms that have fur, have more hair on them. And in that case, it would work. My brother's dog, he lived up in New England a while back and got a dog. He had this big Newfoundland. And then he got a job down in Austin, Texas, and he moved down there with the Newfie. And, you know, Texas is hot. So they said, well, let's go ahead and shave the dog for the summer because that's going to, you know, make him less hot. So they did that. The dog was miserable all summer. And then the next summer, they decided not to shave him because the shaving obviously didn't do any good. And I happened to visit them down in Austin that summer. And it turns out that the dog was much happier. And I happened to be petting the dog, and I put my hand deep in its fur, and there was cool air next to its skin. Because what's happening is when it's hot, it was expanding the thickness of its fur and trapping cold air next to its skin, which in Austin and when he's in the air conditioning was helpful. But we're really talking about when you're cold and this is happening. The opposite there would be when you're cold and your hair follicles move, then you're trapping warm air next to your skin. It just happened to be the Newfie in Austin was doing it in the air conditioning. So it's a little weird, but that's the point, that we can control hair follicles in thermoregulation, which for humans, since we don't really have fur, it doesn't do any good. And then technically it kind of works with our head, but you don't have people's hair standing up on and when they're cold so much, because that hair, it's not fur, it's hair, and it just doesn't quite work the same way. But we still have that holdover. So goosebumps and what hair you do have standing up on end, that's supposed to be a reaction to thermoregulation. But whether we're talking about the smooth muscle that's dilating or constricting blood vessels, or the smooth muscle that's moving hair follicles, Smooth muscle in the skin is very important for thermoregulation. But what else happens in your skin when you have to control body temperature? What's another example of something that happens in your skin besides blood moving in and out or hair standing up? Sweat, right. So what tissue is sweat going to be coming from? Right. So sweat glands, obviously, are glandular tissue. Sweat gland ducts are either simple or stratified cuboidal epithelia, but the gland themselves we could just call glandular tissue. So it's there. So those are some examples of tissues playing into different functions. And let's see, here's some pictures that show about blood flow and heat preservation or radiation. Another thing which is not terribly crucial, well, I shouldn't say terribly crucial, but is a really kind of seemingly minor thing that the skin does is vitamin D synthesis. The molecule vitamin D requires a step where it's exposed to UV radiation. And the only place in your body where you can expose something to UV radiation is in the outer layers of your skin. So this is taking place in the cells of the epidermis, the epithelial layer. And the reason that's the only place where we have it is because those cells can have pigment in them, melanin, which helps to block UV radiation getting deeper into your skin. But as far as a tissue concerned here, the epithelia is where this particular chemical reaction takes place. But really the pigment thing takes us back to protection. Okay. So another thing about that stratified squamous epithelium is that it contains melanocytes, which makes melanin. And then that melanin works its way into the other cells to provide that pigment to block UV radiation. And skin tone, how dark or light skin is, it's really a matter of how much melanin is made. And generally speaking, darker skin tones are associated with people whose ancestors come from more equatorial parts of the world where there's more UV radiation directly from the sun, so they need that kind of protection. And then lighter skin tones are usually associated with more northern latitudes. Think, Swedish blonde, pale skin kind of thing, because there's not a lot of sunlight there, direct UV radiation, so melanin is not that important. Now, I specifically said northern. There's not really a southern component to that. There's not a lot of land mass in the south where people would be in the same kind of situation as people in northern latitudes. People that live in the southern regions like South America or Australia are recent human migrations to that area, those areas. So their skin pigments are more related to where those people migrated from rather than where we find them today. But melanin production, again, is another aspect of protection against UV radiation, which can cause cancer. And it's a component of the epithelial layer again, too. Okay. Now, there are a few other things to kind of consider here, like the dense irregular connective tissue in your dermis is good for protection because it has all that collagen. You won't rip your skin apart, that kind of thing. So that's what I've talked about so far is just some basic introduction to the idea of how you think of the relationship between tissue types and these functions. But do keep that in mind. Think about it for the skin, and then continue to think about it for everything else. So when we're talking about other organ systems, even latent ANP2, it might be that a particular tissue is relevant to the function of that organ because of what that tissue does. So try to keep that thing in mind all along. Okay. So I just want to jump to this functions part here at the end to touch on that idea. As far as the anatomy of the system is concerned, this layers of the skin part here, I want to just mention a few things. First off, the skin is made up of really two layers of tissue. There's the epidermis, represented by this bracket here, and the dermis, represented by this bracket here. That's really the skin. In the book, and in a lot of books like this, they'll also include the hypodermis in a picture like this. The hypodermis technically is not part of the skin, but we usually talk about it in relation to the skin because it's involved in a lot of the functions that we associate with the skin, such as temperature regulation. When blood leaves your skin because you're cold, it gets down into the subcutaneous fat, which is another name for the hypodermis, as well as below that, so that that fat tissue acts as an insulator. Some of the larger structures in the dermis, like hair follicles and some sensory endings, might actually be all the way down in the hypodermis, although they're technically part of the skin. So in the strictest definition, the hypodermis isn't really part of the skin. The skin is really just the epidermis and the dermis, but it's included in a chapter like this because it's related to a lot of the things that happen in the skin. The epidermis is the stratified squamous epithelium. The dermis is connective tissue. Adjacent to the epidermis, there's some areolar connective tissue because there's always areolar connective tissue next to epithelium. And then the rest of the dermis is made up of dense irregular connective tissue, which is shown a little bit later. Personally, I would have put this particular point a little bit later on, but there are two types of skin. There's thin skin and thick skin, which obviously relates to their thickness. Yeah.
Earlier, I was just looking through the book. I wrote a short poem that like goes through the layers of the epidermis, and like kind of summarizes all the layers of the epidermis. If you go to theotherrealm.org, you can see my poem.
If you'd like to at some point share it with, send it to me and I can share it through Blackboard with people. So the reason why I would actually leave the thick and thin skin until later is because it really relates to the layers of the epidermis, which is what you're talking about there, Aaron, right? So there are layers within the epidermis. There's 5 of them. The deepest layer is the stratum basale, which means basal layer. And then going up, there's a stratum spinosum, the stratum granulosum, stratum lucidum, and stratum corneum. There are basically 4 types of cells that you find in the epidermis. One of them is not even in this picture because it's kind of a rare type of cell, but there are melanocytes, which makes melanin, Merkel cells, which are part of the sensory function of skin, and then keratinocytes or keratinocytes, however you want to pronounce it, which we see all 3 of those types that I just named in stratum basale, the basal layer. And then as we move up in this picture, all of the other cells here are keratinocytes. The keratinocytes in the basal layer are dividing. And when they divide, one of the cells from that division stays in the basal layer and the other cell is pushed up into a higher layer. And as new cells are born, they push older cells to higher and higher positions. So these cells way up here at the top, these are keratinocytes, which began life way down here, and they've just been pushed up by newer and newer cells. As the cells move farther and farther away from the stratum basale, they eventually get too far away from the blood supply to survive. And that happens right around in the stratum granulosum. So the stratum lucidum and the stratum corneum are made up entirely of dead cells. These cells cannot get nutrients from the blood, and they can't get rid of waste products through the blood, so they're dead. The stratum granulosum has a high density of pigment, a lot of melanin, and that's where a lot of the UV radiation is blocked. The melanin is made by the melanocytes, but it gets transferred over to the keratinocytes early when they're first made, and it continues on up, and it concentrates in this cells up here. Okay. As the cells get pushed further and further, they also become flatter and flatter. So we get to very flat cells at the top. That's why we call it stratified squamous epithelium. Even though the cells down here at the bottom might be cuboidal or even columnar kind of in shape. And we don't really care about the other shapes. The name is just because there's flat cells at the top. The fourth type of cell, which is not in this picture, is called a dendritic cell. Sorry, that's something left over from last class. A dendritic cell, which is an immune system cell. Whenever a pathogen gets through the skin, the dendritic cell is there basically as a lookout. And it sees bacteria or whatever that's gotten in through the skin, and it can move out of the skin to alert the immune system that something's coming. Dendritic cells are found in a lot of different places, and this is the general name for these. They're found in the skin and then in pretty much all mucous membranes also. And the reason why mucous membranes in the skin is that those things are all immunological barriers. And so if something gets across one of those, it's going to infect our body. So dendritic cells are able to prepare our body for that invasion when it first gets in. You might see these cells called Langerhans cells, or cells of Langerhans. This is what I call a dead white guy name. Okay. Now, really, it should be called an eponymous name, but I prefer dead white guy because it's the name of a dead white male. Okay. Professor Langerhans was the first person to ever describe this particular type of cell in the skin when he was looking at it through the microscope. So he wrote a paper saying, I've discovered this cell. He didn't necessarily name it. He described it. And then some other researcher wanted to talk about that cell again. So he said, the cell that Dr. Langerhans discovered. And then the next person said, Dr. Langerhans cell. And the next person said, Langerhans cell. And the next person, so it just became named after him because he was the one that described it. He's dead, he's white, and he's a guy. Okay? So we call them dead white guy names. Just generally speaking, a lot of things that are named after people, that's the convention from a long time ago. And it's great to boost somebody's ego, but it doesn't really tell students anything. So I'll often point out dead white guy names, and I'll try to give you an alternate name to work from. So I'd prefer to use dendritic cell, which is not that descriptive of a cell name. It doesn't really tell you what it does, but we'll meet dendritic cells in other places when we talk about the immune system in A&P2. And so it's good to understand that they're present in the skin also. If you see Langerhans' name somewhere, just in your mind, substitute dendritic cell in for that. Those are found in the stratum spinosum, which just don't happen to be in the picture here. But that's where you find them. If something gets in through the skin, if it gets down to the stratum spinosum, then the skin's not doing any good to stop it. And so the dendritic cells are there to kind of act as lookouts or sentries, and they can let the immune system know when something's gotten in. So I want to be sure that you're aware of the layers of the epidermis. Now, I would have actually put the thin and thick skin thing after this, because thick skin is thick because it has a really thick layer of stratum lucidum. And thin skin is thin because it pretty much does not have a stratum lucidum. There's a little bit of variation. Okay, it's not just type A and type B skin. There's thick skin, which we associate with the palms of your hands and the soles of your feet. And then there's thin skin, the thinnest of which is found in the scalp and actually the skin right around your lips. So if you put lip liner on, you're covering up some very thin skin. That just happens to be where it is. Has nothing to do with makeup. And then other areas of skin are going to be somewhere in between, probably more towards the thin side, but they might have a little bit of stratum lucidum in them or something like that. Just a word about the thin skin right at the edge of your lips. If you eat spicy food, sometimes you'll feel a little burning right around the edge of your lips, and that's because that skin's so thin that the molecule that makes spicy food spicy can get in through the skin easier there than elsewhere. So you'll feel it really strongly right at that point there. But so that's thick and thin skin. Okay. And so even up here where they're describing it, they say skin that has 4 layers of cells is referred to as thin. And then thick skin has a 5th layer called the stratum lucidum. Okay, so they say it there. There's always some exceptions to things that seem so black and white like that. So there are some rather thin skin areas that have a very minor stratum lucidum, but where it's a significant part of the skin, that's thick skin. And that's really just in the palms of the hands and the soles of your feet. So the soles of your feet is probably obvious. You walk around, you need some barrier there. The palms of your hands, actually kind of for the same reason. Humans don't walk on all 4s anymore, but we still have that thickness in our skin there, which for us is good because it provides a nice thick barrier between whatever we might be grabbing. And of course, my travel mug here isn't anything to worry about, but if I were to grab onto a branch to hang from a tree or something like that, then the thick skin is going to be more protective against being scratched or something like that there. So this describes the different things. In the dermis, I've already kind of said this, there's dense irregular connective tissue and areolar connective tissue. They're referred to as the papillary layers, the areolar connective tissue, and the reticular layer, which is the dense irregular connective tissue. Don't get confused. The reticular layer of the dermis is dense irregular connective tissue. It is not, by any means, reticular connective tissue. Just happen to have the same name, but they're not at all alike. The papillary layer is really these bumps up here that kind of stick up into the dermis, or the epidermis. And the epidermis kind of sticks down in between the papilla. Papilla means a little bump. The pattern of papillae and the corresponding ridges in the epidermis that fit in with them really has a lot to do with the pattern of lines and that sort of thing that you see in your skin. So fingerprints are basically a reflection of the pattern of what the tissue looks like where the papillary layer and the epidermis come together. Okay. And then they talk a little bit about the hypodermis here. And then they get into pigmentation separately. And if you're going to talk about pigmentation, you got to talk about moles. And a disorder of pigmentation in the other direction is this thing where normally pigmented skin becomes very light. It's called vitiligo, which is one of the coolest names of a disorder I've ever heard. Its claim to fame is that Michael Jackson claimed that he had vitiligo, and that's why he became white. It's not, but, well, he probably did have vitiligo, but if he did, it would have been patchy like this. And so probably what happened is he was embarrassed to have vitiligo, so he just made all of his skin lighter to hide the vitiligo patches or something like that. I had a friend in high school with vitiligo. She had it on her legs, which was not really a big problem because she was fairly pale skinned for the most part. But in the summer, when she'd tan, it would get her, her legs would all be blotchy, and she hated it. She was really embarrassed about it. But that's about as bad as vitiligo can be, blotchy skin. Now, it does mean that there's less UV protection in the skin, but you can supplement that by wearing sunblock or hats or clothes or whatever. There is a section in the book here that says diseases, disorders of the integumentary system. I'm not going to even go there because skin disorders are really kind of disgusting, and I don't even want to look at the pictures. But vitiligo I can handle. It's a cool name, and it doesn't look that bad. But as we get into other things in the skin, they can get kind of troublesome. The other section in here is the accessory structures of the skin, which basically means the hair follicles, glands, and the nails, or I should say hair follicles, nails, and glands, which are things that are really kind of extensions of the epidermis down into the dermis layer. So it starts with talking about hair and nails. Hair and nails are very similar to the epidermis in that they have dead cells and they have living cells and they're layers of stuff. It's not the same layers that are in the epidermis, but there are layers of living cells and then layers of dead cells. I don't really care to talk about them in a lot of depth. If you're interested, please do look at them. And there will be a couple of questions here and there about their basic structure, but they're not terribly exciting. Glands in the skin, however, I do want to talk about because, again, glandular tissue is a special kind of tissue. And we already mentioned sweat glands are important for thermoregulation. And there are some other types of glands. Now, in the book, they talk about sweat glands, which are specifically called sudoriferous glands. There are two types of sweat glands, eccrine glands and apocrine glands. And then they talk about sebaceous glands, which are oil glands. Okay, oil is called sebum, and so sebaceous are just glands that secrete sebum or oil. There are actually a couple of other types of glands. That I'd like you to be aware of. Sebaceous and sebaceous glands which secrete oil. And then there's also mammary glands, which of course secrete milk, and ceruminous glands, which secrete wax. Now, not all books have those two types of glands in the skin section, but they are glands in the skin, just in very specific places. So where are mammary glands going to be found? So at the areolar of the breast. And where are ceruminous glands going to be found? Yeah, in the ear canal. Okay. Really, mammary glands and ceruminous glands are variations on sweat glands. Sweat glands filter water out of the blood and a few other components like sodium and chloride and those kind of things. And then it's secreted onto the surface of the skin. Milk glands filter the blood, but then they add milk proteins and lactose to that so that it has some nutritional value. And it secretes it at the skin, just a very specific part of the skin. And ceruminous glands do something similar, but they add wax molecules, which are actually hydrophobic molecules. Wax is a type of lipid, but that's secreted onto the skin, just it happens to be in the ear canal. Oil glands, sebaceous glands, are different from all the rest, the way that they work, and the book talks a little bit about how they work. So really, those are the four main types of glands. I do want to talk a little bit about sweat glands, the two different types that the book talks about. There are eccrine glands and apocrine glands. Now, crine, C-R-I-N, means to secrete. And so like endocrine or exocrine is about secreting into or out of your body. So those two words, eccrine and apocrine, are just words that have to do with secretions. And in fact, eccrine is just a variation of the word exocrine. So instead of an X, it's a C, but it's the same basic thing, which means to secrete outside the body. And those are your basic sweat glands. Okay. When you're hot, your forehead and your palms and whatever get sweaty, and that's the type of gland that does that. Apocrine glands are slightly different. And they're different for a few reasons. One, they have more in them than just your basic sweat. Added to that, filtered out of the blood, the water filtered out of the blood and the other components that make up sweat, have added to it some additional lipids or proteins. Those lipids are usually steroids. They might be related to testosterone or something like that. in men, and then some proteins. Those additional components, when they're secreted onto the skin, can actually be nutritional to bacteria that live in our skin. Okay? And so bacteria will ingest those things, and just like you, when you eat things, they have to get rid of waste products. It's just single-celled organisms like that, their waste products sometimes include odorous molecules. Those particular bacteria that I'm talking about probably don't give off methane, but that's an example of an odorous molecule that some bacteria give off. So those apocrine glands, they're releasing this slightly different type of sweat, are feeding bacteria, which then will give off some odor molecules. So it's the more smelly sweat. And really why it's smelly is because of how it reacts with the bacteria in our skin. It's not inherently smelly itself so much. Another thing about apocrine glands is that they're located where there are hair follicles. So there's a high concentration of them in the armpits, there's a high concentration of them at the groin, and then there's a high concentration of them in the beard, for men who have beards. And then finally, a difference is that apocrine glands are not functional at birth. Eccrine glands are. Eccrine glands are always working. But apocrine glands actually don't become functional until puberty. So the fact that they produce smells, they're found associated with hairier regions like beards and the groin and armpits, and that they're only functional from puberty on, suggests that they probably have some important role to play in reproductive behavior. And I have a weird story to tell you about. Actually, I have a couple of weird stories to tell you about to kind of highlight this. The first one is a story I learned when I was in college. I was actually a psychology major in college, got a minor in biology, before I went on to study the brain in graduate school. But so in one of my biology classes, they were talking about behavioral studies and that sort of thing. So they talked about this one where, and in a lot of behavioral studies that you get in college, the studies are done on college students. So when I was in intro psychology, the graduate students in that department would put up lists and say, I need people to help with a research project, so please come by. It was required of all of the students in intro biology. I had to do 3 research projects for a graduate student, and I get credit for that in the class. And it would be stuff like, come in and read a list of words and then tell me how many of them you remember 10 minutes later, that kind of stuff. I didn't get into any really weird ones, but there was a story of one that my psychology teacher shared, which was college women were asked to come in, and they were rating the attractiveness of pictures of men. Okay. And so they were just shown photographs of men's faces, and they would rate them as attractive. What they were measuring is how that decision was influenced by certain olfactory cues. And so all of these women were given white t-shirts, and they had to smell the white t-shirt before they rated the pictures of attractiveness. All of the women were looking at all of the same pictures, and the difference is half of the women got a brand new, fresh, clean white t-shirt, and half the women got a white t-shirt that had been used by a man. So they were basically smelling apocrine sweat residue. And what they found is the women that were smelling the apocrine sweat residue tended to rate men as more attractive. Okay? So 2 women, one smelling a clean shirt, one smelling a dirty shirt, rating the same guy on average, the one that smelled the smelly t-shirt would tend to rate that guy as more attractive. Okay? It's been a long time since I had that class, and some of the details of that particular study are a little bit hazy in my memory maybe, but that's kind of what was going on there. Another story, which is probably disturbing in a whole different way, has to do with this too. I read an article probably about 5 years ago now about what are called apocrine parties. And in New York City, where teenagers are just completely bored because they can do anything they want, so they're tired of doing all of that stuff, always have to think up new, interesting ways to spend their time. So somebody invented apocrine parties. And the way this works is you go to the party, and in a Ziploc bag, you have, let's say, a white t-shirt that you've worn. Okay? And you put your white t-shirt in a pile. And then you go to another pile and you pick up somebody else's white t-shirt, take a whiff of it. If you like the way it smells, then you meet that person. If you don't like the way that smells, you put it down and you get another one. Okay. So let's say you're a woman, you go there, you have your white t-shirt, you put it in the pile with other women's white t-shirts, and then you pick up a man's white t-shirt and you smell it. If you like it, you get introduced to him. If you don't like it, you smell another one until you find one you like. So in this article, they're interviewing people who have been at these parties and asking them what it's like. And one of the quotes I remember that was great is a woman said, "Oh, they all stink. It's just some of them stink in a different way." So if there's just some quality to the smell of that shirt, they might say, this is kind of interesting. Then they are introduced to that person. And apparently, there's a fairly high bit of compatibility between people when they meet based on their reaction to smells. Now, that's what the story said, high degree of compatibility. What I think really was implied there was a high degree of physical compatibility. I don't think this is the way to meet your lifelong partner necessarily, but for bored 20-somethings in New York City, it's a great way to spend an evening, is to meet somebody that you might be compatible with. And then the story went on to describe different variations. It doesn't have to be, straight men meeting women. There could be men meeting men, women meeting women. You can have just everybody come in, everybody throw their stuff in the same pile, and just start smelling t-shirts, and whoever you meet, whatever. Again, for 20-somethings in New York City, so there you go. But it does suggest that there probably is something about apocrine sweat and reproductive behavior. Some people will describe that as having to do with pheromones, and that drives me crazy because pheromones are something very specific that humans do not deal in. And the reason I have this particular pet peeve is because one of the professors at my graduate school studied pheromones, and she studied salamanders and prairie voles, which are two species that use pheromones. And then there are a lot of insects that use pheromones too. But for a vertebrate, when you're dealing with pheromones, you have a special chemical receptor system which happens to be usually in the nose, but it's not the sense of smell. It's actually similar to the sense of smell, but it's not airborne odors, but rather waterborne odors. And so for salamanders, part of their mating ritual is that the female salamander sticks her nose against the male salamander's skin. And so there's a physical transfer of fluid from his skin to her nose. And then some pheromones that are dissolved in that fluid get into this specialized receptor organ in the salamander's nose, and that has something to tell them about reproductive behavior. Humans don't really have that particular sensory organ. We technically kind of do, but it doesn't really do anything in humans. So we can't really say that we have any sort of pheromone sort of thing to us. But you will hear a lot of people talking about pheromones, and really all they're talking about is the sense of smell, which from a neurobiological perspective is different, but from a Axe body spray kind of perspective, it's the same thing. So yeah, that whole Axe body spray kind of advertising campaign is getting at this idea. Although what's kind of ironic is what I just said is that it's the sweat that really matters, and if you're using Axe body spray, you're basically covering up those scents, and so you're kind of defeating the whole purpose of it.
It would be interesting to do a study that has that compares what people who are really sweaty versus people who just took a shower, and see which preference people have against more.
Yeah, it would be interesting, although there's that kind of study is always going to be kind of confounded by just people have kind of learned that certain perfumes are preferable. It's just, so as a study, that would be actually kind of a tricky one to pull off. But yeah, it would be certainly interesting to get at. But so I just want to go off on a little bit of a tangent there about sweat glands. And there are two different types, and the book talks about them. But I want to be sure that you're aware that there are 4 different types of glands that we associate with the skin. The 2 that are left out from the book, I want to mention because they're in the skin, they just happen to be associated with areas that probably for the person writing this chapter in the book, they figured that mammary glands would be addressed in the reproductive system, and ceruminous glands, I don't know, covered in where you talk about the sense of hearing. Of course, being the person that wrote the chapter about the sense of hearing, I didn't say anything about wax glands, so because they don't have anything to do with hearing. They're there to capture dirt that gets into your ear canal. So, but anyway, so I just want to point those out. And that's the accessory structures of the skin. Okay, I didn't really talk about hair and nails very much because they don't really interest me too much, but do be aware of their structure. There will be some questions about that. None of the big questions that you have on this stuff have to do with the hair follicles or nails, but some of the multiple choice questions might be about that. So that's basically what I want to point out in the skin. For the bone tissue, there's some general instructions about the functions of the skeletal system, and then it concentrates on the structure of bones as an organ, which we want to talk about. And then this section here says bone formation and development is really about how bones grow. And for this chapter, that's what it's basically about, what bones are and how they grow. The next chapter, which is axial skeleton, and then the chapter after that, appendicular skeleton, those two are basically talking about the names of bones, okay, where bones are in the skeleton, what they look like, their features, that kind of thing. And that's pretty much what we're going to concentrate on for the lab component next week. Okay. I do want to say a few things about the structure of bones and how bones grow. First off, there's always a section in these chapters about the classification of bones, which is not terribly crucial, but it has a use, so I want to talk about it for a second. We classify bones based on their characteristics and shape, and really there's 4 major types of bone. The one that we're going to talk about the most, and the reason why we want to sort of set this out, are long bones. Now, long bones aren't necessarily actually long. It's not like we classify them because they're 15 centimeters long or longer, or something like that. We can have some very, very short bones that are classified as long bones because the characteristics they have is that they have a shaft that makes up most of the length of the bone, and then an enlargement on either side, which would be the head of the bone. We'll talk about the structure of long bones in a little more detail and the actual names we use for those parts. But it has nothing to do with their actual measured length. This is showing you the femur, which is your thigh bone. The bones in your lower leg, the tibia and the fibula, are long bones also. The bones in the arm, the humerus, radius, and ulna, those are all long bones too. And those are the bones that really are quite long. But then there's a lot of bones in your hand. So there are 5 that go through the palm of your hand. And then there's 14 more that make up the segments of all of your digits. All of those are long bones. Okay. So obviously you have 2 hands. So there's 2 sets of those. Your feet are laid out kind of the same way. Okay. So there are long bones in what's equivalent to the palm of your hand, but for your foot, what we call the arch of your foot. And then coming off of that, which is in this picture, where the digits are, your toes, they're long bones making up each of the segments of your toes. The little toe, the pinky toe, the fifth digit on your foot, can have some really, really short bones in it, right? And some people have those cute little pinky toes, that kind of thing. There's not much bone there, but it's classified as long because of its basic structure and characteristics. Short bones are not named short bones because they're short relative to long bones. It's really because they're kind of cube-shaped bones. Not always perfectly six-sided cubes, but where they come together and make joints with each other, it's usually the flat face of two bones coming together. Is what we see in between each of these. Pretty much the short bones in your body are in the ankle and the wrist. There are 7 in each of those locations. And of course, you have a left and a right each. So there's 7 in the left foot, 7 in the right foot, 7 in the left ankle, 7 in the right ankle. I did it wrong. Those are wrists, not ankles up there, but you get the point. Those are short bones. Some of those short bones in the ankle, for instance, are much bigger than the long bones in the toes. But again, the names really aren't about the size of the bones, but rather about their characteristics. Then we have flat bones. The example they have here is the sternum or your breastbone. The ribs are also flat, and the bones that surround the brain, the cranial bones, are flat also. Now, flat suggests, flat like one of these floor tiles in here. But really, that's not what we mean by flat. I don't remember where I heard this phrase, but they're not flat like a pancake, they're flat like Kansas. Does that make any sense to anybody in here? I have no idea where I heard that, but I know what it means, so I can use it. So if you look across a pancake, the surface of a pancake is flat, okay? Just level. Okay? If you look across the surface of Kansas, is it flat in the same way as a pancake?
In a certain sense, yes. But,
In no sense is it.
well, it's in the sense of in Kansas, in like
If you're standing on a pancake, you can look across that pancake and see the other end of the pancake. If you're standing on Kansas, you can't look across Kansas and see the other end of Kansas. Because what does Kansas do? Follows the curve of the planet. Okay, so it's flat, more because there's nothing going on there, but it has a curve to it. And the point there is the bones, say, of the cranium are curved, or the bones of, I don't have any handy, but the ribs are curved. And even the breastbone has some curve to it. Not a whole lot. So flat bones have a bit of curve to them. But, so, again, I don't quite remember where that saying came from, but they're flat like Kansas. That they have, meaning that they have a curve to them. So the fourth type here is what we call an irregular bone. And it's basically anything that doesn't fit into the other 3 types there. Okay? Oftentimes they'll have characteristics of multiple types of bones. And a good example is the vertebral bone. The body of a vertebral bone, the part that makes up the vertebral column, which is the opposite side of this vertebral column as I'm pointing at it right there. But that kind of is like a flat bone. Okay, it's got a flat surface, not a flat bone, a short bone. It's got a flat surface where it meets up with the adjacent bone. And then the spinous process sticking out the back is flat. Okay? And sometimes they can have a bit of a curve to them. And then some areas are just different shapes. Okay? So that's sort of a catch-all for anything that isn't one of these other 3 shapes. The book goes on to include another shape, which really, in terms of the other 4, would probably fit into the irregular type bone, but it's reasonable to talk about this because of what is different about this bone. It's called a sesamoid bone, suggesting that it's kind of the shape of a sesame seed. And everybody has two sesamoid bones, which we see there, the kneecaps. Not everybody in the world necessarily has all of the other sesamoid bones that we can describe. But what's special about sesamoid bones is how they develop. They develop because soft tissue calcifies into bone, like the tendon going from the muscles in your thigh that connects to your shin bone. Where that calcifies, that's the patella or your kneecap, and that's a sesamoid bone. There are some other places where sesamoid bones are found, and it's how they develop that they come to be. Okay? So that's kind of a special case there. Now, this isn't terribly important to think about how we classify these bones. I'm not going to necessarily ask you what type of bone is such and such bone. It's more because we're going to talk about bones, and most of what we're going to talk about is going to be in reference to long bones, how bones, the structure of bones and how bones grow. All of the examples, with a couple of exceptions, are going to be long bones, just because they have some special characteristics that the other bones don't share. And the other bones are kind of like certain parts of long bones, and I'll explain that in a while. So when we talk about bone structure, we're going to concentrate on the anatomy of a long bone. Okay. So earlier when I was describing long bones, I said they had a shaft and they have a head at either end. The name for the shaft of a long bone is the diaphysis, okay, which is the label right here in the middle. This says diaphysis, not that you can read it from where you're sitting. And then the head, the end at either extreme of the bone, is called the epiphysis. So this is the femur that we're looking at here, and the epiphysis up here sometimes can be called the head of the femur, but epiphysis is kind of a word that refers to the head. There's two epiphyses, that's the plural, and they're usually described in long bones, because long bones are in your limbs, as proximal and distal epiphyses. So for the femur, the end that's at the hip joint is the proximal epiphysis, and the end that's at the knee joint is the distal epiphysis. Now, there's a bracket in between epiphysis and diaphysis at either end, which is labeled metaphysis. The metaphysis isn't always included when we talk about long bones, but it is sort of this transition where the shaft of the diaphysis kind of widens out and the epiphysis comes in. Also, a defining characteristic of the diaphysis is that its wall is made up of a thick, compact bone wall, like we see in this bone here. That compact bone thins out, and so the outside edge of the epiphysis has a very thin shell of compact bone, making it kind of a smooth outer surface. But then the inside of the epiphysis is mostly spongy bone. And so the metaphysis can also be said to describe where that transition is, from the thick, compact wall of the diaphysis to the thin, compact shell of the epiphysis, and where the spongy bone kind of comes in. And if we're going to put a bracket around it, it could kind of be where the wall is getting thinner and where the spongy bone is starting to come in that area. Another thing about the metaphysis is it represents where in the bone it was growing longer when somebody was in the process of growing. And there's a little line right here through the metaphysis in the end that's been exposed or cut open here. That's the remnant of the growth plate, okay? That's bone, it's calcified because this bone is full grown, but when the bone was shorter, that's where the bone was actually growing longer. And we'll talk about growth processes in a little bit. Okay? But that's also in the metaphysis. Some sources won't even bother mentioning the metaphysis because it's not a very crucial part. So we'll talk about the diaphysis or the shaft and the epiphyses or the head at either end. Okay? So that's the structure of a long bone. Any other bone is basically like the epiphysis of a long bone. It's going to have a very thin shell of compact bone on the outside, and the center is mostly going to be spongy bone. Spongy bone looks like sponge. I pointed out to you when we were talking about bone matter, bone tissue on Monday. But because it has all those holes, all that space in it, it's lighter than compact bone would be. So the majority of your bones are just spongy bone with just a thin outer shell of compact bone to give them a outer surface. So what we see here for the epiphysis is what pretty much all the other bones in your body kind of look like. They don't have anything like the diaphysis. The diaphysis of long bone is basically meant to be weight-bearing. That's not exactly relevant to all of your long bones, but as you're standing on your legs, then the weight of your body is mostly being borne on the compact bone wall of those bones there. The empty space in the middle of the bone is filled with bone marrow. In the diaphysis for an adult, the bone marrow is yellow, which means that it's adipose tissue. And in some bones, the bone marrow is red in the epiphyses, and it's red because it's making blood cells, the majority of which are red blood cells. So it has a reddish color to it. In a full-grown adult, there's actually very little active red bone marrow in any of the bones, and one of the places where there is active red bone marrow is in the head of the femur, which would be here. But there's actually not that much red bone marrow throughout the body. In a fully mature adult. There's a lot of it in children, but it sort of starts to turn into yellow bone marrow or adipose tissue as we get older. This is showing a little bit of detail of what the tissue looks like up close. This is showing a specific section of a flat bone. Not that it's terribly different from anything I've talked about. It has a thin shell of compact bone on the outside, and then the center is spongy bone. It's in here because there's technically a word for that spongy bone and flat bones that's slightly different. I'm not going to say it because I think I pretty much mispronounce it every time I say it, and also because as far as I'm concerned, it's just spongy bone. So we'll just refer to it that way. Something we're going to talk about next time in learning about the structure of specific bones will have to do with bone marking. So I'm going to skip over this. And so this is just some more stuff about what particular markings are. Bones are living tissues, so they're going to have cells in them. And there are 4 types of bone cells. The first 3 here kind of represent a family group. There are osteogenic cells, which are basically the stem cells that form bone tissue. They develop into osteoblasts, and blast sometimes refers to a stem cell, but more in the sense that this isn't the final mature type of cell. Osteoblasts are known most because they form the bone matrix, the solid extracellular matrix of bone, okay, which is the what's the word I'm looking for? Calcium phosphate crystal structure that I talked about last time. That's produced by the osteoblasts. Osteoblasts can become the fully mature osteocyte, which is responsible for maintaining the tissue. What basically happens, and we'll see this in the growth process, bones grow because osteoblasts make bone matrix, and the bone gets bigger in whatever direction it's growing. Some of the osteoblasts will stay within the bone matrix, and the bone matrix will form around them, and they'll mature into the osteocyte so that they can live in the bone matrix and maintain that for the rest of the life of the bone. But not all osteoblasts necessarily become osteocytes. Okay. But it's basically grandpa, the parent, and the offspring cell here. They're all related. The 4th type of cell over here is not part of that family. It's called an osteoclast, which is very similar sounding to osteoblast. But what osteoclasts do is they take apart the bone matrix. So osteoblasts make bone matrix, osteoclasts take it apart. There's this ongoing dynamic of building and taking apart bone matrix because it's how we store calcium as a mineral in our body. And so those two cells are always playing at that homeostatic mechanism.
So when someone has a is basically osteoporosis, like the correctity of the osteoblast?
I think it's either the osteoclasts are working too hard and taking apart the bone, or the osteoblasts are not working well enough and building it back up. I can never quite remember exactly what's going on there. For calcium homeostasis, it's usually all about the osteoclasts. When you need to store more calcium in your bones, osteoclasts slow down their production so they don't release as much calcium. And when you need more calcium in your blood, osteoclasts become more active and release more calcium. The osteoblasts just sort of chug along and do their job. But as far as osteoporosis is concerned, I think it is really a problem with the osteoclasts, that they're a little overactive, but I might be wrong about that. It's been a while since I really looked at that closely. Now, another thing about osteoclasts, why they're not part of this family that, like with the other three, is that they're actually derived from white blood cells. And if you notice in this picture, the cell has multiple nuclei. And when you have a cell with multiple nuclei, that basically tells you that it's several cells that have all merged together. So there's some types of white blood cells that merge together to make up this sort of supercell, which is the osteoclast. And white blood cells, certain white blood cells, are responsible for chewing up debris and foreign matter in your body. We call those macrophages. And so osteoclasts are related to that in that they kind of chew up the bone matrix. Okay, so they're related cell types. They work on similar processes, but this is specifically working on the bone. And it's several cells that have all merged together into one big cell to do that job. So those are the types of cells. When you look at the structure of compact bone, it's highly organized, and in these columnar structures, column structures, which we're looking down on right here, the center is actually kind of empty. There's not bone tissue right in there, but rather there are blood vessels and nerve fibers that are going through that. And then it's surrounded by rings of bone matrix. All of the little dots that are in here, let me enlarge that picture. So all of these little gray spots in here, or there are more black spots down here, those are the osteocytes that are in the bone matrix. And they form these rings surrounding the central canal where the blood vessels and nerves are. And the whole thing, that structure that kind of looks like a tree that's been cut in half so you can count the rings, is called an osteon. Osteons, being fairly circular in structure, don't fit together perfectly well. So there can be these kind of triangular spaces between them, like this. There's still bone matrix in there. It's one continuous field of bone matrix, but this matrix isn't organized into rings around an osteon. And then also there's going to be layers of bone matrix wrapped around the entire bone, which we see this outermost, and it'll just continue on. It'll be the outer surface of the whole bone. For where we see spongy bone mostly in just a thin, compact bone shell, that shell might really be mostly just these circumferential lamellae, or layers of bone matrix that run around the outside of the cell, around the outside of the bone, without a whole lot of this sort of thing in there. The nerves and blood vessels that run through the central canals are interconnected from one osteon to another, suggested in this side view here, or we can see that there are blood vessels that go from one to another across and into the central space of the bone right there. The edge of the tissue right here, this is actually spongy bone. That's what spongy bone looks like. Less organized than the structure of compact bone, lighter spaces within the bone, that kind of thing. Nope. And they talk about spongy bone here. Some sources will refer to it as cancellous bone. I actually can't remember what that word technically means, but it's talking about this structure of bone here. If we look at one of the little spicules of bone, it is organized into layers of bone matrix with osteocytes and all that. It's just not highly organized into the osteons, and all the other lamellae is compact bone tissue. And then it goes on to talk about that there's blood and nerve supply to that. So those are what bones are. Bone formation or growth is an important part of this chapter. The way that this chapter starts out, I would have actually put this first little bit a little later on the page, but what it's saying is the fetal skeleton starts as a series of cartilage templates, kind of like placeholders for where the bones are going to be, and it's cartilage tissue, specifically hyaline cartilage. That's the fetal skeleton. It kind of harkens back to other organisms that don't have bony skeletons. Okay? All land animals, mammals, birds, reptiles, and amphibians have bony skeletons. Fish sometimes have bony skeletons and sometimes have cartilaginous skeletons. The bony skeleton fish you're probably familiar with because you might have eaten fish and you've got bone in the meat or something like that. Though that type of fish is where the first land animals kind of came from. Having a bony skeleton supports the weight of the tissues in the body so that without the water surrounding the animal anymore, it's able to exist on land. Cartilaginous fish don't really work that well on land, and so they're not really the source of land animals. But we still have cartilaginous fish that didn't go through that particular route for evolution. And the probably best known cartilaginous fish is a shark. Okay? Sharks actually don't have bony skeletons. They have bony kind of teeth, all the better to eat you with, my dear, and that kind of thing. But really their skeleton is cartilage. And in the fetus, we still see there's this cartilage skeleton there. It's just for humans or any land animal, that cartilage is going to develop into bone. So there are two major ways that bone of the fetal skeleton develops. One is called intramembranous ossification, and the other one is endochondral ossification. And both of these, the word ossification means bone growth. It comes from the Latin word for bone, which is os. Intramembranous is actually talking about bones that don't develop out of cartilage. So I would have put that cartilage template thing after this part of the book, but the book didn't do it that way. Intramembranous ossification is where the embryonic connective tissue, mesenchyme, directly calcifies into bone. And that happens for the bones of the skull and the clavicles, which are your collarbones. All of the other bones in your body developed through endochondral ossification, which is cartilage becoming bone. Now, there's a reason why the skull and the clavicles do this rather than the other. I'm not 100% sure of what that reason is, but we can actually kind of get at an idea of where it might come from. What's important about the bones of the skull and the shoulders, especially having to do with childbirth, which is kind of when we're talking about these bones solidifying, calcifying. What's important about the skull and the collarbones? Right. That's the hard part about giving birth, is getting the skull and the shoulders through the birth canal. So I can't say with 100% certainty that that's why those bones develop this way, but those bones are still soft at that point in development, which your mother is very happy for. Okay. All of the other bones in your body have probably fully calcified by the time of birth. Okay. And once the shoulders have gotten through, then the rest of everything kind of really folds up. The joints are really, really loose. And so there's not a whole lot of problems with the other bones getting out, even though they're fully calcified at that point. Okay. That's my guess as to why those particular bones develop this way, whereas the other ones develop the other way. Okay. This kind of gives a basic idea of how the process works. Somewhere in the mesenchyme, some of the cells become osteoblasts, which lay down bone matrix, and the bone matrix spreads and becomes spongy bone. Blood vessels are growing through it, and we don't see it in this picture, but red bone marrow develops within that. And then at the edge, where there are all these osteoblasts, they're laying down the compact bone shell on the outside, but that forms the bone there. And then mesenchyme, beyond the part that's becoming the bone, ends up becoming the other connective tissues that are the outside covering the bone. It's called the periosteum. Okay, so that all develops there. Endochondral ossification is when this cartilage template for the bone ends up calcifying to become the bone. Now, it's not that the cartilage turns into bone exactly, but rather the cartilage is replaced with bone. So cartilage has cartilage cells called chondrocytes, and bone has bone cells, one of which we just met were osteocytes, but there's osteoblasts and that sort of thing. The chondrocytes end up sort of dying off, and the cartilage matrix is calcified, and osteoblasts and osteocytes grow into that. For long bones, the process is a bit involved. The diaphysis starts developing first, and where calcification starts and bone starts to grow in to replace the calcium is called the primary ossification center. And that grows out to be the diaphysis. And then, but the epiphyses don't grow in that process. They develop a secondary ossification center, and they become their own kind of bone. That's sort of suggested here in the picture. Okay, so here's the diaphysis growing in, and the epiphysis stays as this uncalcified cartilage at this point. And then a secondary ossification center grows in here, and the cartilage that was at the end here becomes the epiphysis. Cartilage will remain on the outside surface until the bone's fully grown. Some of that cartilage remains, and it becomes what we call the articular cartilage, which is part of the joint that this is going to make with its neighboring bone. Some of the cartilage remains in between the epiphysis and the diaphysis, and that's going to become what we call the epiphyseal plate, or more commonly the growth plate. And that cartilage is what's going to grow into, what's going to grow as the bone gets longer. Okay. Now, in this picture, they just show one epiphysis going through this process, but the other epiphysis is doing the same thing. There are two secondary growth centers, two secondary ossification centers, one in each epiphysis. Okay. The primary one is the first one that makes the diaphysis. All other bones, besides long bones, their development is pretty much like what we see for the epiphysis here. So there's not primary and secondary ossification centers in other bones. There's just an ossification center. And the cartilage template of whatever that bone is calcifies and is replaced by bone at that ossification center. And most of the center of that bone is just spongy bone like the epiphysis. What's going on with the diaphysis is unique to long bones. Here they talk about how bones grow longer, and the cartilage that's left over after the epiphysis grows in next to the diaphysis then grows. There's some cartilage that stays just plain old cartilage for a while, but some of the cells start to proliferate, and it gets thicker, and those cells get bigger, and then the cells die off, and the matrix starts to calcify, and bone tissue replaces it. So in a way, this is endochondral ossification too, but the cartilage has to grow to make the bone longer at that plate. So all of these layers are going to eventually become bone as they progress through these different parts. And eventually at the end, when the bone's fully grown, the resting cartilage, or reserve zone as they call it in this picture, that ends up calcifying too. And what you see left over is that thin line of bone like we saw in the metaphysis earlier. In some bones, it's not really visible. It's there, but it's so thin that you can't really see it with the naked eye very easily. You usually can see it with an x-ray because it's a little bit denser than the spongy bone around it, so it stands out in an x-ray. But in a sawn open bone like what was drawn there, or that bone over there, you can't see it. There's no obvious line in that epiphysis because it's so thin. And this is just showing you a shorter bone that gets longer through this process. Now, in the book, they say how bones grow in diameter, and they just refer that as modeling, and then they mention bone remodeling. I want to introduce another term to you, which is a different type of bone growth, and that is appositional bone growth. The word appositional is close to the word oppositional. Okay, to oppose something with an O means to be against it, like you're opposed to student fees being increased. Apposition, to be opposed to something, is to be against it also, but to be physically against it. When appositional growth is taking place at the edge of the bone, okay, and that mostly takes place in a process which we can see in a video. So I'm going to the video content here in Blackboard. And we just want to scroll down past the introductory chemical. Okay, I have the cell in the wrong place. But then we get into tissues. Oh, there's cells. Cells, tissues, skin, more skin, skeletal system. And then after that broad skeletal system one, there's another one that has to do with this kind of growth. This, though it doesn't actually say it anywhere in the picture, is showing us appositional bone growth. It's only 45 seconds long. Let me just play it real quick. Let me start that over.
Bones grow through the process of appositional growth, the formation of new bone on the surface of older bone or cartilage. Osteoblasts beneath the periosteum lay down bone to form ridges around the blood vessel. The blood vessel lies in a groove between the ridges. The groove is transformed into a tunnel when the bone built on the adjacent ridges meets. The periosteum of the groove becomes the endosteum of the tunnel. Osteoblasts from the endosteum lay down bone to form a new concentric lamella. The production of additional concentric lamellae fills in the tunnel and completes the formation of a new osteon.
Okay. So, just as they're showing us here, appositional growth is when, come on, stupid thing, there we go, is when the outside edge of the bone grows thicker and will surround blood vessels until the two ridges meet together and they, come on, where is it? There it is. They make a continuous piece of bone, and then the inner lining here, what's called the endosteum at this point, grows in, and rings of bone matrix are laid down, forming, forming a new osteon. Okay. Now, this kind of happens at the edges of bones just in general as they're getting bigger. When your long bones are growing longer, all of the other bones have to get bigger too because your entire skeleton grows. So appositional growth is kind of happening at that point, which is what the book is referring to as modeling. But appositional growth happens later in the body too. Where particular points of stress are found on bones, the osteoblasts that do this sort of thing will be stimulated. And so where a muscle attaches to a bone, when it pulls on the bone with the tendon, that'll stimulate this kind of growth, and the bone will get a little bit thicker right there. And the bone markings that we're going to talk about next week sort of have to do with that. For example, the humerus, which is your upper arm bone, has a bump on it right about here, about halfway down on the lateral surface, called the deltoid tuberosity. It's where the deltoid muscle attaches. That bump is there because every time you lift your arm up, a little bit of stress is put on the bone at that point. Now, eventually the bone grows thick enough to handle the stress of pulling on it with the deltoid bone muscle. But as you first start to use your muscles, that's going to start to stimulate growth at specific points on the bone where it needs to be thicker because it's where the muscle's attached. And that's part of what appositional growth is. So next time we're looking at the bone markings, we'll be thinking about how they are where muscles attach or something like that. And that'll be a nice little transition into the idea of next time we're going to be looking at the bone markings. I want to hand out this to you, which is the laboratory material for what we're doing next week. This is a list of all of the bones that you need to know by name. There's actually not that many bones, but what makes this a lot of information is that you're going to be responsible for knowing the bone markings. So I want to hand this out to you now so you can look at it. You can look at your book. Some of you have devices, whether it's your phones or your computers or whatever, where you can pull the book up. But if you don't have access to that, you might want to look at this stuff in relation to the axial and appendicular skeleton chapters ahead of time, just so you have some reference. I skipped over a table in the book earlier that was bone markings because, one, we're going to talk about that more, and also I'm giving you a different list. I just found this online. It's a more complete list of the names of things that are bone markings. So I've stapled that on here to have with the list of the bones you need to know. I'm going to hand this out to you now. Be sure to keep it and have it with you next week because it's going to be part of what we're doing next week to get to know the bones. But I'd like you to, in the meantime, if you don't have access to the book in class through some sort of device, maybe one or two. Okay. Then go ahead and look at this and just, I don't know, connecting your mind to the material that's in the book so you know what to study. And I'll talk some about how you're going to use this information next week and how to study from it for the sake of the practical study. I only have, looks like 4, maybe 5 more copies of this. And there are some people that aren't here today that will be here on Monday. So these are for them, which is to say I'm not going to have more copies of this to hand out. If you forget to bring this next week, then you don't have it on hand. So please hang on to this and bring it back into class on Monday for when we're doing the stuff with the skeleton. Any questions about this kind of introduction through the material in the skin and bones chapters? Anything? If you don't have any questions, that's it for today. And I'll see everybody on Monday.